5. Periodic classification of elements. In class 6 we have learned that matter around us is present in the form of elements, compounds and mixtures, and the elements contain atoms of only one type. Do you know how many elements are known till date? At present, 114 elements are known to us. Around the year 1800, only 30 elements were known. All these had seemingly different properties. As different elements were being discovered, scientists gathered more and more information about the properties of these elements. They found it difficult to organize all that was known about the elements. They started looking for some pattern in their properties, on the basis of which they could study such a large number of elements with ease. Figure 5.1. Imagine you and your friends have found pieces of an old map to reach a treasure. Would it be easy or chaotic to find the way to the treasure? Similar chaos was there in chemistry as elements were known, but there was no clue as to how to classify and study about them. 5.1. Making order out of chaos. Early attempts at the classification of elements. We have been learning how various things or living beings can be classified on the basis of their properties. Even in other situations, we come across instances of organization based on some properties. For example, in a shop, soaps are kept together at one place while biscuits are kept together elsewhere. Even among soaps, bathing soaps are stacked separately from washing soaps. Similarly, scientists made several attempts to classify elements according to their properties, and obtain an orderly arrangement out of chaos. The earliest attempt to classify the elements resulted in grouping the then known elements as metals and nonmetals. Later further classifications were tried out as our knowledge of elements and their properties increased. 5.1.1 Dobereiner's Triads. In the year 1817, Johann Wolfgang Dobereiner, a German chemist, tried to arrange the elements with similar properties into groups. He identified some groups having 3 elements each, so he called these groups triads. Dobereiner showed that when the 3 elements in a triad were written in the order of increasing atomic masses, the atomic mass of the middle element was roughly the average of the atomic masses of the other 2 elements. For example, take the triad consisting of lithium Li, sodium Na, and potassium K with the respective atomic masses 6.9, 23.0 and 39.0. What is the average of the atomic masses of Li and K? How does this compare with the atomic mass of Na? Given below table 5.1 are some groups of 3 elements. These elements are arranged downwards in order of increasing atomic masses. Can you find out which of these groups form Dobereiner triads? You will find that groups B and C form Dobereiner triads. Dobereiner could identify only 3 triads from the elements known at that time, table 5.2. Hence, this system of classification into triads was not found to be useful. Johann Wolfgang Dobereiner 1780–1849. Johann Wolfgang Dobereiner studied as a pharmacist at Münchberg in Germany, and then studied chemistry at Strasbourg. Eventually he became a professor of chemistry and pharmacy at the University of Jena. Dobereiner made the first observations on platinum as a catalyst and discovered similar triads of elements, which led to the development of the periodic table of elements. 5.1.2 Newlands Law of Octaves. The attempts of Dobereiner encouraged other chemists to correlate the properties of elements with their atomic masses. In 1866, John Newlands, an English scientist, arranged the then known elements in the order of increasing atomic masses. He started with the element having the lowest atomic mass, hydrogen, and ended at thorium, which was the 56th element. He found that every 8th element had properties similar to that of the first. He compared this to the octaves found in music. Therefore, he called it the Law of Octaves. It is known as Newlands Law of Octaves. In Newlands Octaves, the properties of lithium and sodium were found to be the same. Sodium is the 8th element after lithium. Similarly, beryllium and magnesium resemble each other. A part of the original form of Newlands Octaves is given in table 5.3. Do you know? Are you familiar with musical notes? In the Indian system of music, there are 7 musical notes in a scale: sa, re, ga, ma, pa, ga, ni. In the West, they use the notations do, re, mi, fa, so, la, T. The notes in a scale are separated by whole and half-step frequency intervals of tones and semitones. A musician uses these notes for composing the music of a song. Naturally, there must be some repetition of notes. Every eighth note is similar to the first one and it is the first note of the next scale. It was found that the law of octaves was applicable only up to calcium, as after calcium, every eighth element did not possess properties similar to that of the first. It was assumed by Newlands that only 56 elements existed in nature, and no more elements would be discovered in the future. But, later on, several new elements were discovered, whose properties did not fit into the law of octaves. In order to fit elements into his table, Newlands adjusted two elements in the same slot, but also put some unlike elements under the same note. Can you find examples of these from table 5.3? Note that cobalt and nickel are in the same slot, and these are placed in the same column, as fluorine, chlorine, and bromine, which have very different properties than these elements. Iron, which resembles cobalt and nickel in properties, has been placed far away from these elements. Thus, Newland's law of octaves worked well with lighter elements only. Questions. 1. Did Dobereiner's triads also exist in the columns of Newland's octaves? Compare and find out. 2. What were the limitations of Dobereiner's classification? 3. What were the limitations of Newland's law of octaves? 5.2 Making order out of chaos. Mendelev's periodic table. Even after the rejection of Newland's law of octaves, many scientists continued to search for a pattern that correlated the properties of elements with their atomic masses. The main credit for classifying elements goes to Dmitry Ivanovich Mendeleev, a Russian chemist. He was the most important contributor to the early development of a periodic table of elements wherein the elements were arranged on the basis of their fundamental property, the atomic mass, and also on the similarity of chemical properties. Dmitry Ivanovich Mendeleev 1834–1907. Dmitry Ivanovich Mendeleev was born in Tobolsk in western Siberia, Russia on 8 February 1834. After his early education, Mendeleev could join a university only due to the efforts of his mother. Dedicating his investigations to his mother, he wrote, "She instructed with example, corrected with love and traveled with me to places spending her last resources and strength. She knew that with the aid of science without violence, with love, but firmness, all superstitions, untruth and errors can be removed." The arrangement of elements he proposed is called Mendelev's periodic table. The periodic table proved to be the unifying principle in chemistry. It was the motivation for the discovery of some new elements. When Mendeleev started his work, 63 elements were known. He examined the relationship between the atomic masses of the elements and their physical and chemical properties. Among chemical properties, Mendeleev concentrated on the compounds formed by elements with oxygen and hydrogen. He selected hydrogen and oxygen as they are very reactive and formed compounds with most elements. The formulae of the hydrides and oxides formed by an element were treated as one of the basic properties of an element for its classification. He then took 63 cards and on each card, he wrote down the properties of one element. He sorted out the elements with similar properties and pinned the cards together on a wall. He observed that most of the elements got a place in a periodic table and were arranged in the order of their increasing atomic masses. It was also observed that there occurs a periodic recurrence of elements with similar physical and chemical properties. On this basis, Mendeleev formulated a periodic law, which states that the properties of elements are the periodic function of their atomic masses. Mendelev's periodic table contains vertical columns called groups, and horizontal rows called periods. Table 5.4. Table 5.4 Mendelev's periodic table. Mendelev's periodic table was published in a German journal in 1872. In the formula for oxides and hydrides at the top of the columns, the letter R is used to represent any of the elements in the group. Note the way formulae are written. For example, the hydride of carbon, Ch4, is written as R4 and the oxide Co2, as ρ2. 5.2.1 Achievements of Mendelev's periodic table. While developing the periodic table, there were a few instances where Mendeleev had to place an element with a slightly greater atomic mass before an element with a slightly lower atomic mass. The sequence was inverted so that elements with similar properties could be grouped together. For example, cobalt, atomic mass 58.9. appeared before nickel, atomic mass 58.7. Looking at table 5.4, can you find out one more such anomaly? Further, Mendeleev left some gaps in his periodic table. Instead of looking upon these gaps as defects, Mendeleev boldly predicted the existence of some elements that had not been discovered at that time. Mendeleev named them by prefixing a Sanskrit numeral, Eka1, to the name of preceding element in the same group. For instance, scandium, gallium and germanium, discovered later, have properties similar to Eka boron, Eka aluminium, and Eka silicon, respectively. The properties of Eka aluminium predicted by Mendeleev and those of the element, gallium, which was discovered later and replaced Eka aluminium, are listed as follows. Table 5.5. This provided convincing evidence for both the correctness and usefulness of Mendeleev's periodic table. Further, it was the extraordinary success of Mendeleev's prediction that led chemists not only to accept his periodic table, but also recognize him as the originator of the concept on which it is based. Noble gases like helium, He, neon, Ni, and argon, Ar, have been mentioned in many a context before this. These gases were discovered very late because they are very inert and present in extremely low concentrations in our atmosphere. One of the strengths of Mendeleev's periodic table was that, when these gases were discovered, they could be placed in a new group, without disturbing the existing order. 5.2.2 Limitations of Mendeleev's classification. Electronic configuration of hydrogen resembles that of alkali metals. Like alkali metals, hydrogen combines with halogens, oxygen and sulfur to form compounds having similar formulae, as shown in the examples here. On the other hand, just like halogens, hydrogen also exists as diatomic molecules, and it combines with metals and non-metals to form covalent compounds. Activity 5.1. Looking at its resemblance to alkali metals and the halogen family, try to assign hydrogen a correct position in Mendeleev's periodic table. To which group and period should hydrogen be assigned? Certainly, no fixed position can be given to hydrogen in the periodic table. This was the first limitation of Mendeleev's periodic table. He could not assign a correct position to hydrogen in his table. Isotopes were discovered long after Mendeleev had proposed his periodic classification of elements. Let us recall that isotopes of an element have similar chemical properties, but different atomic masses. Activity 5.2. Consider the isotopes of chlorine, Cl35 and Cl37. Would you place them in different slots because their atomic masses are different, or would you place them in the same position because their chemical properties are the same? Thus, isotopes of all elements posed a challenge to Mendeleev's periodic law. Another problem was that the atomic masses do not increase in a regular manner in going from one element to the next, so it was not possible to predict how many elements could be discovered between two elements, especially when we consider the heavier elements. Questions. 1. Use Mendeleev's periodic table to predict the formulae for the oxides of the following elements: K, C, A, Si, Ba. 2. Besides gallium, which other elements have since been discovered that were left by Mendeleev in his periodic table? Any two. 3. What were the criteria used by Mendeleev in creating his periodic table? 4. Why do you think the noble gases are placed in a separate group? 5. 3. Making order out of chaos, the modern periodic table. In 1913, Henry Moseley showed that the atomic number of an element is a more fundamental property than its atomic mass as described below. Accordingly, Mendeleev's periodic law was modified and atomic number was adopted as the basis of modern periodic table, and the modern periodic law can be stated as follows. Properties of elements are a periodic function of their atomic number. Let us recall that the atomic number gives us the number of protons in the nucleus of an atom, and this number increases by 1 in going from one element to the next. Elements, when arranged in order of increasing atomic number JUD, lead us to the classification known as the modern periodic table. Table 5.6. Prediction of properties of elements could be made with more precision when elements were arranged on the basis of increasing atomic number. Activity 5.3. How were the positions of cobalt and nickel resolved in the modern periodic table? How were the positions of isotopes of various elements decided in the modern periodic table? Is it possible to have an element with atomic number 1.5 placed between hydrogen and helium? Where do you think should hydrogen be placed in the modern periodic table? Table 5.6 Modern periodic table. As we can see, the modern periodic table takes care of three limitations of Mendeleev's periodic table. The anomalous position of hydrogen can be discussed after we see what are the bases on which the position of an element in the modern periodic table depends. 5.3.1 Position of elements in the modern periodic table. The modern periodic table has 18 vertical columns known as groups and 7 horizontal rows known as periods. Let us see what decides the placing of an element in a certain group and period. Activity 5.4. Look at the group 1 of the modern periodic table, and name the elements present in it. Write down the electronic configuration of the first three elements of group 1. What similarity do you find in their electronic configurations? How many valence electrons are present in these three elements? You will find that all these elements contain the same number of valence electrons. Similarly, you will find that the elements present in any one group have the same number of valence electrons. For example, elements fluorine F and chlorine Cl belong to group 17. How many electrons do fluorine and chlorine have in their outermost shells? Hence, we can say that groups in the periodic table signify an identical outer shell electronic configuration. On the other hand, the number of shells increases as we go down the group. There is an anomaly when it comes to the position of hydrogen because it can be placed either in group 1 or group 17 in the first period. Can you say why? Activity 5.5. If you look at the long form of the periodic table, you will find that the elements Li, B, C, N, O, F, and Ni are present in the second period. Write down their electronic configuration. Do these elements also contain the same number of valence electrons? Do they contain the same number of shells? You will find that these elements do not have the same number of valence electrons, but they contain the same number of shells. You also observe that the number of valence shell electrons increases by 1 unit, as the atomic number increases by 1 unit on moving from left to right in a period. Or we can say that atoms of different elements with the same number of occupied shells are placed in the same period. Now, Mg, Al, Si, P, S, Cl and Ar belong to the third period of the modern periodic table, since the electrons in the atoms of these elements are filled in K, L and M shells. Write the electronic configuration of these elements and confirm the above statement. Each period marks a new electronic shell getting filled. How many elements are there in the first, second, third and fourth periods? We can explain the number of elements in these periods based on how electrons are filled into various shells. You will study the details of this in higher classes. Recall that the maximum number of electrons that can be accommodated in a shell depends on the formula 2n2, where n is the number of the given shell from the nucleus. For example, K shell 2 multiplied by 1 2 equals 2. Hence the first period has 2 elements. L shell 2 multiplied by 2 2 equals 8. Hence the second period has 8 elements. M shell 2 multiplied by 3 2 equals 18. But the outermost shell can have only 8 electrons, so the third period also has only 8 elements. The position of an element in the periodic table tells us about its chemical reactivity. As you have learned, the valence electrons determine the kind and number of bonds formed by an element. Can you now say why Mendeleev's choice of formulae of compounds as the basis for deciding the position of an element in his table was a good one? How would this lead to elements with similar chemical properties being placed in the same group? 5.3.2 Trends in the modern periodic table. Valency. As you know, the valency of an element is determined by the number of valence electrons present in the outermost shell of its atom. Activity 5.6. How do you calculate the valency of an element from its electronic configuration? What is the valency of magnesium with atomic number 12 and sulfur with atomic number 16. Similarly, find out the valencies of the first 20 elements. How does the valency vary in a period on going from left to right? How does the valency vary in going down a group? Atomic size. The term atomic size refers to the radius of an atom. The atomic size may be visualized as the distance between the center of the nucleus and the outermost shell of an isolated atom. The atomic radius of hydrogen atom is 37 pm picometer. 1 pm equals 1012 m. Let us study the variation of atomic size in a group and in a period. Activity 5.7. Atomic radii of the elements of the second period are given below. Period II elements, BBONLC. Atomic radius PM, 88 111 66 74 152 77. Arrange them in decreasing order of their atomic radii. Are the elements now arranged in the pattern of a period in the periodic table? Which elements have the largest and the smallest atoms? How does the atomic radius change as you go from left to right in a period? You will see that the atomic radius decreases in moving from left to right along a period. This is due to an increase in nuclear charge, which tends to pull the electrons closer to the nucleus, and reduces the size of the atom. Activity 5.8. Study the variation in the atomic radii of first group elements given below and arrange them, in an increasing order. Group 1 elements, null RBCSK. Atomic radius PM, 186 152 244 262 231. Name the elements which have the smallest and the largest atoms. How does the atomic size vary as you go down a group? You will see that the atomic size increases down the group. This is because new shells are being added as we go down the group. This increases the distance between the outermost electrons and the nucleus so that the atomic size increases in spite of the increase in nuclear charge. Metallic and non-metallic properties. Activity 5.9. Examine elements of the third period and classify them as metals and non-metals. On which side of the periodic table do you find the metals? On which side of the periodic table do you find the non-metals? As we can see, the metals like Na and Mg are towards the left-hand side of the periodic table, while the non-metals like sulfur and chlorine are found on the right-hand side. In the middle, we have silicon, which is classified as a semi-metal or metalloid because it exhibits some properties of both metals and non-metals. In the modern periodic table, a zigzag line separates metals from non-metals. The borderline elements boron, silicon, germanium, arsenic, antimony, tellurium, and polonium are intermediate in properties and are called metalloids, or semi-metals. As you have seen in Chapter 3, metals tend to lose electrons while forming bonds, that is, they are electropositive in nature. Activity 5.10. How do you think the tendency to lose electrons will change in a group? How will this tendency change in a period? As the effective nuclear charge acting on the valence shell electrons increases across a period, the tendency to lose electrons will decrease down the group. The effective nuclear charge experienced by valence electrons is decreasing because the outermost electrons are further away from the nucleus. Therefore, these can be lost easily. Hence, metallic character decreases across a period and increases down a group. Non-metals, on the other hand, are electronegative. They tend to form bonds by gaining electrons. Let us learn about the variation of this property. Activity 5.11. How would the tendency to gain electrons change as you go from left to right across a period? How would the tendency to gain electrons change as you go down a group, as the trends in the electronegativity show? Non-metals are found on the right-hand side of the periodic table towards the top. These trends also help us to predict the nature of oxides formed by the elements because it is known to you that the oxides of metals are basic and that of non-metals are acidic in general. Questions. 1. How could the modern periodic table remove various anomalies of Mendeleev's periodic table? 2. Name 2 elements you would expect to show chemical reactions similar to magnesium. What is the basis for your choice? 3. Name 3 elements that have a single electron in their outermost shells. B 2 elements that have 2 electrons in their outermost shells. C 3 elements with filled outermost shells. 4. Lithium, sodium, potassium are all metals that react with water to liberate hydrogen gas. Is there any similarity in the atoms of these elements? B. Helium is an unreactive gas and neon is a gas of extremely low reactivity. What, if anything, do their atoms have in common? 5. In the modern periodic table, which are the metals among the first 10 elements. 6. By considering their position in the periodic table, which one of the following elements would you expect to have maximum metallic characteristic? Georgia GE as CB. What you have learned. Elements are classified on the basis of similarities in their properties. Dobereiner grouped the elements into triads and Newlands gave the law of octaves. Mendeleev arranged the elements in increasing order of their atomic masses, and according to their chemical properties. Mendeleev even predicted the existence of some yet to be discovered elements on the basis of gaps in his periodic table. Anomalies in arrangement of elements based on increasing atomic mass could be removed when the elements were arranged in order of increasing atomic number, a fundamental property of the element discovered by Moseley. Elements in the modern periodic table are arranged in 18 vertical columns called groups, and 7 horizontal rows called periods. Elements thus arranged show periodicity of properties including atomic size, valency or combing capacity and metallic and non-metallic character. Exercises. 1. Which of the following statements is not a correct statement about the trends when going from left to right across the periods of periodic table? A. The elements become less metallic in nature. B. The number of valence electrons increases. C. The atoms lose their electrons more easily. D. The oxides become more acidic. 2. Element X forms a chloride with the formula XCly, which is a solid with a high melting point. X would most likely be in the same group of the periodic table as a NaBmgCadSi. 3. Which element has a 2 shells, both of which are completely filled with electrons? B. The electronic configuration 2, 8, 2. C. A total of 3 shells, with 4 electrons in its valence shell. D. A total of 2 shells, with 3 electrons in its valence shell, it twice as many electrons in its second shell as in its first shell. 4. A. What property do all elements in the same column of the periodic table as boron have in common? B. What property do all elements in the same column of the periodic table as fluorine have in common? 5. An atom has electronic configuration 2, 8, 7. What is the atomic number of this element? B. To which of the following elements would it be chemically similar? Atomic numbers are given in parentheses. N7F9P15AR18. 6. The position of 3 elements A, B and C in the periodic table are shown below. Group 16, Group 17. A. B. C. A. State whether A is a metal or non-metal. B. State whether C is more reactive or less reactive than A. C. Will C be larger or smaller in size than B? D. Which type of ion, cation or anion, will be formed by element A? 7. Nitrogen atomic number 7 and phosphorus atomic number 15 belong to group 15 of the periodic table. Write the electronic configuration of these two elements. Which of these will be more electronegative? Why? 8. How does the electronic configuration of an atom relate to its position in the modern periodic table? 9. In the modern periodic table, calcium atomic number 20 is surrounded by elements with atomic numbers 12, 19, 21 and 38. Which of these have physical and chemical properties resembling calcium? 10. Compare and contrast the arrangement of elements in Mendeleev's periodic table and the modern periodic table. Group activity. We have discussed the major attempts made for classifying elements. Find out from the internet or library about other attempts to classify elements. We have studied the long form of the periodic table. The modern periodic law has been used to arrange elements in other ways too. Find out what are these.